Okay, let's have a look at binomial expansions. So firstly, the word binomial means two terms. So bi, two, like a bicycle, two wheels, and nomial, term or name. So two terms. So for example, a binomial expression would be something like 3 plus 2x. So that's a binomial expression. It's got two different terms. And expansion is if we're multiplying out brackets. So the reason we call this a binomial expansion is it's two terms usually raised to a power. So for example, to the power of 5. So if we were to do this out by hand, it would take ages. Okay, so there is a shortcut, but to see what's happening, let's start with an example. So I'm going to start with a fairly basic example. I'm going to use a plus b. So I've used a plus b because a and b could stand for any numbers. Okay, so it doesn't matter what numbers these are or what terms. Okay, we're just going to look at what pattern is happening. I'm actually going to color code them as well. So the first term will be in red and the second term in blue. So let's start with a nice easy one, a plus b squared. So in order to multiply this out, we don't need any fancy trick because it doesn't take that long. So I'll use my area model. So just grab this one that I've got prepared and I'll start to get my answers. So start with a times a is a squared, a times b is ab. B times a is ba, or if we write it in alphabetical order, again it's ab. And then b times b is b squared. So my answer is I've got an a squared at the start. Then we can see I've got two like terms here. I've got ab in there twice. Okay, so ab plus ab is 2ab. And then finally I've got a b squared as well. Okay, so let's look at this in terms of our colors. So first of all, I've got an a squared, the first term squared. Then I have plus 2, and again I have an a. This time it's to the power of 1. And then I have a b, again to the power of 1. And finally, I have a b squared. Okay? So, we can't really see any pattern happening after one example. So let's look at another example. So, now let's look at a plus b. So, a plus b. And this time I'll do to the power of 3. So a plus b to the power of 3 means a plus b multiplied by a plus b multiplied by a plus b. So we can't do that all in one go. Usually when we are multiplying three things together, we'll multiply two of them together first and then multiply our answer by the last one. So for example, if we did 2 times 3 times 4, you'd probably do 2 times 3 first in your head to give you 6, and then multiply 6 by 4 to get 24. So we'll do the same thing here, multiply these two together first, but we've actually already done that here. So instead of doing it again, I can just multiply my result by the last bracket. Okay, so I'll get my area model again. I have one ready again for this one to save a bit of time. So I'll bring that up and we'll get our answers for this one. So a times a squared is a cubed. A times 2ab is 2a squared b. A times b squared is ab squared. Then I've got b times a squared is a squared b. And you notice I'm always writing them in alphabetical order. Just makes it easier. Then b times 2ab is 2ab squared. And b times b squared is b cubed. Okay, again, if you look closely, on the diagonal we have an a squared b and an a squared b there. So we've got like terms on that diagonal. Then the next diagonal we have ab squared and ab squared. So again, we have like terms on the diagonals. So in total, we've got an a cubed. Then I have a squared b and a 2a squared b, which makes 3a squared b. Then I've got more like terms, 2ab squared and ab squared is 3ab squared. And finally, a b cubed. So let's look a little bit closer at what's happening here. So to start with, I've got an a to the power of 3. And you'll notice in the next term, I have an a squared. And the next term, I have an a, or an a to the power of 1. And the last term, there's no a. Then if we look at the b's, the first term has no b. The second term has a b to the power of 1. The third term has a b to the power of 2. The fourth term has a b to the power of 3. And then I have these numbers here. So there's a 3 in front of this term and a 3 in front of this term. Now if we look a little bit closer at both of these, we could actually say that there is a b to the power of 0 here as well. Because b to the power of 0 just means 1. And 1 times a cubed is just a cubed. And the same as that, we've got an a to the power of 0 at the end here. Because a to the power of 0 is 1, and anything times 1 just stays the same. So if we look at the powers a little bit closer, you can see we start with power of 3, which matches our expansion. And then power of 2, power of 1, power of 0. So we're going in descending powers. So we can write the first term in descending powers. Then if we look at the second term, starting it with the power of 0 and going power of 1, power of 2, power of 3. So it's going in ascending terms, going upwards. Okay, but then we have these numbers as well. Okay, and these feel a bit random. There doesn't seem to be a pattern. And if we look at this one a little bit closer as well, we can see the same thing is happening. There's actually a b to the power of 0 here, and there's actually an a to the power of 0 there. So we have the expansion is power of 2, and it goes power of 2, power of 1, power of 0. And the second term goes the other way. Power of 0, power of 1, power of 2. But again, there's a number here, or a coefficient. Okay? Now there's actually coefficients on all of these terms, but this one is just 1, and that one is just 1. And down here, this one is just 1, and that one is just 1. So is there a pattern happening with the coefficients, the numbers in front, the numbers in black, with these numbers? Is there a pattern? And the answer is yes, there is. Okay, and we can find that pattern using Pascal's triangle. Okay, so you'll notice in our first example, the coefficients went 1, 2, 1. And you'll notice the third row in the triangle has 1, 2, and 1. And in our cubed example, the coefficients were 1, 3, 3, 1. And in our triangle, we have 1, 3, 3, 1. And if you were to do another expansion to the power of 4, you'd find that the coefficients are 1, 4, 6, 4, and 1. So all the numbers in each row of this triangle represent the coefficients. Okay, and you can do, if you like, you can stop the video and do a plus b to the power of 4. And you'll notice that you get 1 as your coefficient, then 4, then 6, then 4, and then 1. Okay, if we actually, I may as well finish this. So if that's going to be a, it's going to be a to the power of 4, a to the power of 3, a to the power of 2, a to the power of 1, or just a, and then a to the power of 0 at the end. And the b's will go b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 3, and b to the power of 4. So you can do out that expansion and see that this is what you get. Okay, so it follows the same pattern, and you will see that you get the coefficients 1, 4, 6, 4, 1, which are the numbers in the next row. So we can use Pascal's triangle to tell us the coefficients for each expansion. So you'll notice that when the power was squared, when we were using squared, we used this row of the triangle. So this is a plus b squared, say. Now it doesn't have to be a plus b, it can be anything plus anything. So I'll use a and b to represent that it could be any numbers. And when it was cubed, it used this row. The coefficients were the numbers in this row. And when it was to the power of 4, the coefficients were the numbers in that row. So if we did to the power of 1, obviously to the power of 1, we don't need to multiply by anything. So there would just be two terms, a plus b, and their coefficients are both 1 because there's no number in front, or there's a hidden 1 in front. And if I do anything to the power of 0, I just get the answer 1. So a plus b to the power of 0 is just 1. So obviously it's just a term 1, so the coefficient is 1. So we can number these rows but we need to start at 0 because that's what the power corresponds to. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So if I was to do an expansion, let's say a plus b to the power of 9, I could write my a in descending powers, my b in ascending powers, and then I can use these numbers as my coefficients. Okay? So let's look at our original example. The original example was 3 plus 2x to the power of 5. So I'm going to do this using Pascal's triangle. So 3 plus 2x to the power of 5. Again, to make it a little bit clearer, I'm going to color code it. So my first term is a 3. So I'm going to start with the power of 5 and write it in descending powers. So I'm going to start with 3 to the power of 5, and then leave a bit of space, 3 to the power of 4, and then 3 to the power of 3, 3 to the power of 2, 3 to the power of 1, and 3 to the power of 0. I'm just going to space these out a little bit because I know I'm going to be probably a bit tight for space here. Okay. So now I'm going to go to my second term, which is 2x. Now, because there's a letter and a coefficient and a variable here, I'm going to put this in brackets. So the whole thing is power of 0. The whole thing is power of 1, power of 2, and so on. I'm going to work my way up in ascending order. Okay, and I should probably put these in brackets as well, just to make it clear that we're multiplying. Okay, so now all I'm missing is the coefficients. So I could kind of multiply it all out and find the coefficients that way, but I can use a shortcut, just go to Pascal's triangle. Okay, I go through the rows 0, 1, 2, 3, 4, and 5. So I'm doing power of 5, so let's use this row. And you'll notice for each row as well, if I'm doing power of 5, it goes 1 and then 5. Power of 6, it goes 1 and then 6. Power of 8, 1 and then 8, and so on. So you can quickly look at the row and see which one you should use. I'm doing power of 5, and I can see it starts with 1 and then 5. So this is my row. So the numbers are 1, 5, 10, 10, 5, 1. So they will be the coefficients for my expansion. So I'll start with a 1 in front of this one, 5 in front of that one, 10 there, 10 in front of that one, then a 5 in front of that one as well, and then a 1 in front of that one. Don't forget to add in your pluses to separate the terms. And that is my expansion done. All I need to do now is simplify it. So I've done the expanding part, now I need to simplify. So let's look at each term separately here. So to start with, I've got a 1 times 3 to the power of 5, and 3 to the power of 5 is 243, times 2x to the power of 0, and anything to the power of x is 1. Anything to the power of 0 is 1. So the total there is just, actually I'll leave that, and underneath it I'll write the total is 243. Okay, my next term, I've got 5 times 3 to the power of 4, which is 81, and times 2x to the power of 1, which is just 2x. So in total there, I have 5 times 81 times 2 and then times x. So 5 times 81 times 2 is 810, and I've got my x at the end. Then I go on to the next term. So this time I've got a 10 multiplied by 3 cubed, and 3 cubed is 27, multiplied by 2x all squared, which gives me 8x squared. So I've got 10 times 27 times 8x squared, or in other words, sorry, that's not an 8, that should be a 4. 2x squared is 4. So in total, this will give me 1080x squared. Then I go to my next term. I've got a 10 times a 3 squared, which is 9, times 2x cubed, which this time gives me 8x cubed. Okay, so I have a 10 multiplied by 9 multiplied by 8x cubed, which is 720x cubed. Okay, next term, I've got a 5 multiplied by 3 to the power of 1, which is 3, multiplied by 2x to the power of 4, which is 16x to the power of 4. So in total, 5 times 3 times 16 is 240x to the power of 4. And finally, I've got my last term, which is 1 times 3 to the power of 0, which is also 1, times 2x to the power of 5, which is 32x to the power of 5. So 1 times 32 is 32 with my x to the power of 5. Okay, so there is the expansion fully finished and simplified. So we started with the first term, and we wrote this term in powers of descending power, starting with the expansion power, so 5, 4, 3, 2, 1, and 0. Then the second term we did the other way around, 0, 1, 2, 3, 4, and 5. And then to find the coefficients, we just look at Pascal's triangle. So to the power of 5, we look at this row here. So 1, 5, 10, 10, 5, and 1. 1, 5, 10, 10, 5, and 1. And then to finish it off, we just need to simplify.